Okay, here is the first video for Chapter 11. Chapter 11 is entitled Theories of Covalent Bonding. So this in some ways is a revisit of Chapter 7 and 8, the quantum mechanics chapters. And it's interesting in a way in that if you think about this, kind of putting the course in perspective, we did quantum mechanics kind of in the middle of the course after we had kind of talked a little bit about some of the basics really, and quantum mechanics threw a major monkey wrench into the modeling of this, and that it ended up kind of modeling the electrons as though they were waves, and there was an awful lot of these results which were essentially driven from the math of quantum mechanics, and it gave rise to some of the geometries we started looking at before we got into the geometries in Chapter 10 of molecular shape. So we got into geometries of the electrons' configurations, which were known as orbitals, and we did a little bit of kind of quantum math with that, and filling up the orbitals and making some predictions based upon an element's size and how many orbitals they had, how many valence electrons they had, and all that. Then we kind of went away from quantum mechanics and did some more kind of traditional theories. And the VSEPR theory that we covered in Chapter 10 was a really nice theory that is more classical. I mean, in some ways you can kind of envision the electron clouds as though they are in a certain spot, and the electron cloud location ends up repelling the other clouds and helping to form up the molecular shape. So now here we are in Chapter 11, and we're going to kind of combine the two concepts, the concepts of quantum mechanics that we covered in 7 and 8, and basically kind of combine that with everything that we've kind of learned already in Chapters 9 and 10 about bonding. And now we're going to actually talk about the theories of covalent bonding now in Chapter 11. Okay, so I want to kind of drop back for a second and just to recap the whole bit about orbitals. Okay, and we'll have our three dimensions here. And if you recall, we have s orbitals, p orbitals, d orbitals, and f orbitals. And I'm going to kind of focus on s and p for the moment. In fact, almost everything in this chapter we talk about, almost everything, or I should say the significant conceptual bits, you can really get, I think, by just focusing on the s and p orbitals. We will talk a little bit about d orbitals as well, because they're important, especially for the 5 and 6 electron groups for the molecules that have those 5 and 6 orientations. But truly the important concepts you can get just by studying the S and P's. So most of this video, by way of intro, I think I'm just going to talk about the S and P's. So if you remember, when n equals 1, we have the s orbital. So the one s orbital exists for the top row of the periodic table. And then as you go down, we add in some others. So at the second one, you've got the 2s and the 2p, and that's all that's allowed when n equals 2. And then when n equals 3, you've got the 3s, the 3p, and the 3d. If you remember, the 3d doesn't really show up until in the periodic table until you get to the 4th level. But even though it's there, it is there, but it's of higher energy. It's higher in energy than even the 4s. But I draw it in there as well. And then et cetera, it goes from there. Now, what I want to kind of revisit here are the actual shapes of these orbitals. And I'm really just going to focus on S and P. The S shape, if you remember, is spherical. It's a sphere centered around the center, which essentially says that when an electron is in an atomic orbital in one of these S's, would be 1s, 2s, 3s, etc., it tends to have a probability density that is spherical in nature, with the highest density at the nucleus. Okay, so that's what 1s would look like, and 2s would look a little larger, and then 3s, etc., like that. But they're all spherical. Is the key point. Okay. Then we talked about the p orbitals, and I'm going to draw those again. And it turns out this will be pretty important to what we're about to talk about. So the p orbitals, if you remember, a p orbital has 3 possible orientations. So one orientation is around the y-axis. Another orientation is around the x-axis, and the third orientation is around the z-axis. It's always a little tricky to draw. Okay, and so that's the picture of what the p orbital kind of looks like. All right, what this chapter is about is theories of bonding that take into account these orbitals, and in fact, in particular, the orbital shapes. And if you remember, the whole concept of orbital is really answering the question of where is the electron. And when we were talking about just atoms, the where is the electron was really a question that we asked with respect to a single atom. And I even talked about this in the wave equation. The wave equation that we solved, Schrodinger's equation that we solved, was really about where is the electron with respect to its nucleus. There was really only kind of two charged particles in the simplest model, and that's what gave birth to the, well, it could be in a number of different places, and it's all quantum and all that. When we're talking about bonding, though, the question is still kind of where is the electron. But now in a bond, we know that the where question is actually now a question that we ask in relation to two different charged centers, the electron with respect to the two nuclei. And that changes the math. And this is actually probably one of the key things here, is that the whole quantum mechanics is still valid in molecules, but the math gets much more complex. But what that kind of means is that we're allowed to actually, or say, what has been done in a theory known as valence bond theory, is to embrace all the quantum mechanics, basically all the underpinnings of quantum mechanics, embrace that, but then modify it a bit to explain mathematically as well as in geometric models the whole question of where are the bonding electrons. So remember, in the atom, it was basically where is the electron with respect to the atom. In a molecule, it's where are the paired electrons with respect to the two nuclei. Okay, and so that's kind of and it's, again, it's a math trick. It really is just a bit more complicated math because we have extra charged bodies. But what falls out is a model that's very similar to the atomic orbital models that we encountered in chapter 7 and 8. Okay, pretty long intro to this to the subject, but that's kind of the important. It's really important to know that the valence bond theory that we're going to spend most of the time talking about in chapter 11, it really falls out of the same basic math that we encountered in chapter 7 and 8, but it's more complicated because now we're talking about where are the bonding electrons, not just where is the electron with respect to a single atom. All right, now there are a couple of principles I want to cover about this before I end this. It's kind of the intro video. But there's a couple of central themes to the valence bond theory, and by the way, I'm just going to abbreviate that VB theory. So the valence bond theory, and it's right out of the text. It basically says it relies on the fact that essentially the Pauli exclusion principle, where opposite spins, electrons with opposite spins, must say a molecular orbital or an orbital that we're talking about here reflecting a bond. Can comprise of at most two electrons, and those two electrons have to be opposite spin. Okay, that isn't really that as important as some of the other considerations, but that's one of the central themes of VB theory. The second, and I think maybe the most important, is that the orbitals involved in a molecule. Well, actually, this is probably maybe even maybe this is the first theme. Let's see what the third point is. Yeah, actually, the third point is probably most important. Let me do the third point first. Third point is something called hybridization, and is the central theme of VB theory. And what it essentially says is that in an atom, the orbitals are shaped the way I just drew them. The S and the P are shaped the way I drew them, where the S is spherical and the P I have these kind of loops along the three dimensions. The key aspect of VB theory is that in a molecule, and actually in particular, for the valence electrons in a molecule, the valence electrons involved in bonding in a molecule, the orbitals are kind of a mix. They do something which is called hybridization, meaning the S and the P orbitals, the spherical shape and the loopy shape, of S and P kind of combine to form something that is a hybrid between, it's something like a little bit of an S and a little bit of a P. And in fact, it kind of looks like, and I mean looks like mathematically, again, it looks kind of like a little knobby thing on one half and a little knobby thing on the other half. And so it kind of, really at a glance, it looks more like a P than it does an S. But the S characteristics tend to make a little bit more of a density near the nucleus. If you remember, S is one of the characteristics of the S orbital is the electron is always closest to the nucleus. But that's not the case in P. And in fact, in the case of a pure P orbital, the density of the electron at the nucleus actually drops to 0. That's why it kind of curves in like that. But the sp hybrid, which is the most important hybrid that we're going to talk about, is a mix that kind of has a different shape. All right, and then the last important principle that I'll cover, and you'll see this theme over and over again, is that in molecular bonding, in valence bonding, in covalent bonding between valence electrons, the shape of the orbitals involved tend to maximize an overlap. They tend towards a geometry that results in a maximum overlap of electron configurations between the two atoms, between the bonding atoms. This will become more clear as we draw some pictures. So I just want to introduce that, and those are kind of the key themes of BB theory. Okay, I'm going to stop this one, and I'm going to pick back up on a couple more introductory comments, and then we're going to get right into the hybrid orbitals, which is really, again, the kind of the meat of the whole